My name's Andy Barrett. A lot of people have collaborated and contributed to this. I'm going to kick off. I'm going to talk about some data access and a little bit about format of some of the ICESat-2 data in a very general sense. Then I'm going to talk about some tools that we use to access and work with some of the ICESat-2 data. And then I'm going to hand over to JP here. He's going to talk about slide rule, which you were introduced to yesterday by Tyler. So what I want to do first is kind of set the lay of the land and talk a little bit about how data access fits into a simple kind of data workflow. This is a diagram from R. So I'm blanking on the name of the person who put it together, but it describes a simple data workflow, right? And I think it describes most of the workflows that we kind of employ in our day-to-day activities. We import data, whether that's loading data from the hard drive on our local laptop or workstation, or we can access data from the cloud. We do something with that data. If it's field data, we've got a lot of cleaning to do, dealing with battery failures, missing data, things like that. Even if it's data that we're getting from NASA or some other data center model data, we might have to do some cleaning on that, tidying it up so that we can work with other data sets that we've brought in. And then we enter kind of the analysis phase, the transforming of the data, calculating averages, whether it's spatial averages, temporal averages, calculating new values, new variables from that. We visualize that data, and then we apply some model, whether some simple statistical model or we use it in a more complex dynamical model. And then ultimately we communicate our findings. What I want to talk about is just this small import section here and how we can utilize the various resources that we have, whether it be the cloud or whether it be data stored at the DACs, and kind of suggest some ways of combining those two data sources together within this simple workflow. So I'm going to skip over the question of when to cloud and just go straight into some of these solutions. So this is kind of probably, if you've never used the cloud, this is how you work, right? You download data to a local machine, and you go through that entire workflow on your local machine. And the way that NASA Earth Data Cloud is set up is that you can grab data from the cloud and download it to your local machine. You can grab data from one of the DACs and download that to your local machine. But there's going to be times when that data is either too large and you don't want to spend the time downloading it. If you download model output, sometimes it can take days, if not weeks, to get all the variables for all the time steps you need. So you want to avoid doing that. You might not have the connectivity, and you might not have the storage for all that data. So being able to have some alternative to this local workflow is really helpful in those situations. So here's what I'm calling a hybrid solution. Maybe we want to grab analysis data and we're interested in reanalysis data only over the Greenland ice sheet. Well, we can do a lot of the subsetting of that data, a lot of the pre-processing of that data in the cloud, because that data is in the cloud. And then once we've done the tidying step, the subsetting and the reprocessing, we can then download that smaller set of data to our local machine and work with it there. And there might be other data in other data centers that we can just download as we normally would. So this is what I'm calling a hybrid solution. So we do some of the work in the cloud. And then we have all in the cloud. And this is probably what we're going to focus on this week here, because we have Cryo in the cloud available to us. We don't We're not having to pay for it. It's free at the point of service, which is a great service that we can take advantage of. And we can run the whole workflow through in the cloud. But I think it's worth thinking that there are alternatives to this, because it might come that we're not always going to have access to cloud computing, or we might have limited resources in order to utilize that cloud computing. So we need to recognize that we can mix and match and build workflows to solve that that problem. Okay, and then I will just mention at the end here, cloud-based services. Slide Rule is a service. There are other services like NASA's Harmony, and even OpenDAP is a kind of service that allows us to subset and crunch down data, not on our local machines, but then download some of that data to our local machines. So don't forget about cloud-based services. In fact, I think cloud-based services are going to become more and more important, and we're going to utilize it more and more in our science. So with that said, I want to show you perhaps the most basic way of accessing data, just to accessing ICESat-2 data in order to set the scene, and that is NASA's Earth Data Search. Who here has used or interacted with NASA's Earth Data Search? Okay, right. So almost, let's say 75% of people, right? So this allows you access to all of NASA's data holdings, both in the cloud and also stored and archived at the DACs. And the data that's in the cloud is indicated by this little cloud, Earth Data Cloud symbol on the side here. Now, if you want to see all the data, all of NASA's data that's in the cloud, I note that Sentinel-1 here and Sentinel-2 is not strictly NASA data, it's European Space Agency data, but NASA hosts it on Earth Data Cloud. We can click this Available in Earth Data Cloud button, and that will subset or filter all the data that is in the cloud and available to you to work there. Now, there's what we got over 2,900 data sets that are in the cloud currently. There's more going in there each day. I'm going to subset that down using the keyword NSIDC, and I know that ICESat-2 and ICESat data from NSIDC is what we have in the cloud. So this is a quick way of getting to that ICESat-2 data. There is 47 data sets for ICESat-2 that are in the cloud. You'll notice here that this is the ATLO3 global geolocated photon data. There's actually two versions of that, version 5 and version 6 down here. That's because the DACs generally archive the two current versions. So if you need to go back and check some work with an earlier version, you can always go get that data. If you need to go to earlier versions, there are ways of getting that data, but hopefully that's not something that you need to do. Let's say we want ATLO3. We can click on that card there, and that will bring up a list of ATLO3 granules. I'm interested mostly in Arctic data. So we can select a view for the Arctic, and there we go. We've got a list of data granules that are in the cloud for ATLO3. I'm just going to select the first 4 here, so that we don't end up having to do a lot of work. And then what you want is to get the links to that, right? You want to get the data onto your machine or onto your cloud instance. So we can click download, and that will do some work. And you'll see that we end up with these two panels here. There's an option here for direct download, and that's really what we're interested in if we're working in the cloud. Direct download. If you're in a AWS compute instance in US West 2, the Amazon region where all of NASA's data is stored, you can directly access that data that's stored there without having to download it to your compute instance. You can think of that essentially as reading a file from your hard drive. It's not quite the same, and I'll explain some differences there, but you can think of it in that way. I'm going to say I want to download this, so I'll click on that, and right. So that's returned the 4 granules that I selected. You can see here that they have HTTPS links. This is what you'd use if you want to download your data to your local laptop. You can even get a download script, a Python script that you can then run on your computer to download that. I'm interested in direct access in Amazon S3 buckets. And when I click on that, you'll see that the links now have an S3 bit at the front here, right? That's the address for that particular granule in Amazon's S3 storage. And I can use those links to then download or work with that data in my Amazon compute instance, so on your Cryo in the Cloud hub. You're going to need some more information here, which is AWS credentials. You don't need to read that. These are secret, but I'm not expecting you to remember all these characters here, so I'll be impressed if you do. They only last for an hour, so it's pretty safe. But this is the extra piece of information that you need to access data in the cloud. Now, there are ways of working with this directly, and I will direct you to a tutorial that we have here. This is under the using NASA Earth Data Search to discover cloud host data. If you click on this link here, NASA Earth Data Cloud Access Guide, this will explain to you how to use the AWS command line client to access that data directly from an instance. I'm not going to go through all of that today, because what I want to describe to you are some of the more programmatic access patterns that have been developed. Initially, Earth Access, which is, I like to think of as the Swiss Army knife for accessing NASA data. It deals with authentication, searching of data sets, searching of granules, and then accessing those granules, whether you're on your local machine or in the cloud. That was developed by Luis Lopez, who's here. Then I'm going to talk a little bit about IcePix, which you've already heard from Jessica, a product of one of these Hackweeks, and a really great tool for you to interact with and access data, specifically ICESat-2 data. And then JP is going to talk about slide rule. So let's move to Earth Access, and I'll show you how to use that. Pull my script up here. Okay, so right, there we go. Okay, so I'm going to take you through a very simple workflow for searching for data using Earth Access. And as always with all Python, we import the libraries we need to use. I'm going to import Earth Access. That's the main tool we're going to use. I'm going to import Xarray. I'm going to import it as with a short name XR. That's a standard short name for Xarray. I'm going to, and then I want to display it. So I'm going to use hvplot, and I'm just going to use the Xarray part of hvplot, and then I'm going to import pretty print, just because I want to be able to display some Python objects in a nice way, and pretty print is a part of the standard library that allows you to do that. So that's importing. And then the first step, you know, we all have Earth Data login credentials. The first step we need to do when working with NASA data is to authenticate using Earth Data login. The nice thing about Earth Access is that takes care of all of that for you just by typing earthaccess.login. What it also does is when you're in the cloud, it will set up the S3 secret credentials that I just showed you. So you don't even need to think about those. It happens. Now, it has a number of ways of setting up authentication. We're recommending you use a .NET-RC file. It can also use environment variables. And if you haven't set any of that up, then you can just enter your Earth Data username and login. So many ways to access that. And then we're just going to run a query. We're going to do the same query that we did using Earth Data Search. I'm going to search data sets. And we're going to just do keyword for ICESat-2. And it goes out and it's found 69 ICESat-2 data sets, right? Or data sets that have the keyword ICESat-2. We can look at that, each of those collections or data sets, whichever way you want to think about them, just by, and I'm going to just look at the first 10. And this is where I'm going to use this pretty print method. And I'm going to use, so we've just been introduced to objects, right? The query that gets returned, what gets returned as query is a list, and it's a list of collections or data sets. Each of those collections or data sets is an object, and that object has a whole number of different methods associated with it. I'm going to use the summary method, which prints a nice summary of the data, and I want to just add some keywords to preprint just to make it look a little better. So I'm indenting it by 4 spaces. I want to sort the keys. Collections is an object, but it's essentially a dictionary. So I just want to sort the keys to that dictionary. And then just for clarity, I'm going to print an extra line in there. And what do we do? I said sort index, and it's actually sort dicts. Right. So we can now see what's returned by collection summary. It returns a concept ID, which is a unique identifier to each NASA data set. It tells us something about the file type that data is stored in, HDF5 in this case. Gives us a bunch of links that allow us to access the data. It gives us a short name, ATL03. and it tells us the version. This top collection is actually an NSIDC DAC. This collection below here is in the cloud, and when we have cloud data, it returns all this cloud info, so credential endpoints and ways of getting to that data on S3. Next thing, let's just only look for stuff or data stored in the cloud. So we're going to run another search. Search data sets. And we're going to search for the same keyword. And now we're going to say we want just cloud hosted data. Goes off, does its thing, and it returns 29 data sets, right? These are the 29 ICESat-2 data sets that are stored in the cloud that you have access to. Now, Earth Access is using exactly the same tool, CMR, that Earth Data Search is. It's just that we can do it from the notebook. Now, that's how we search for the data sets, and we've decided that I've decided for you that we're gonna look for ATL06 granules. That's the land ice height, and we want to search for actual files that contain the data. In order to do that, we use the search data method, right? Not search data sets, we're searching for data now. And we're going to search using short name. Okay. And we want to make sure that we're getting the latest version. I actually think if you don't need to be explicit entering the version, I think if you don't specify it, it will return the latest version, I think. We can confirm that later. We want to make sure that we're getting data sets that are in the cloud. And then we're going to set a spatial filter bounding box. Right? So we're looking for a square defined by a minimum and maximum extent in longitude and a minimum maximum extent in latitude. I'm actually going to look for data that's over the Juno ice field, or just coming off the Juno ice field. So we've got these are the latitudes. I'm just copying them because I can't remember them. Right. I'm just going to look for those in this date range, which is March and April of 2020. And sometimes these searches can end up returning a lot of data. So we're going to limit the count to 100. You'll see we don't actually have to do that in this case, right? I've made an error here, and I made the same error last night. So I know what I did, which was I defined the bounding box as a list, and Earth Access expects that to be expressed as a tuple. A list in Python, square brackets, a tuple, it has parentheses. And it's found 4 granules. We can display information about those granules using a Python function called display. And here, if those of you familiar with Python will recognize this particular idiom, but it's called a list comprehension. It's like a for loop, but what it does is in the for loop, it returns something to a list, right? So you define a list comprehension using the square brackets, and then you put the thing you want to return, in this case, display R at the beginning, and you say for every R in the list of results that we got returned from Earth Access search data, return that display object. And that then returns a whole bunch of information here. We can see the actual file name for that data set. We can see the size, 3 megabytes in this case. We can see that it's cloud hosted. And then there are a couple of little diagrams that show the data, both the spatial extent of that data and also some of the data. In this case, you can see that the first result doesn't have a great deal of data in it. So those are useful little thumbnails to look through. That's right. So we've looked for a collection. We've chosen that collection. We've looked for granules within that particular collection over a certain area within a certain time frame. Now we want to actually be able to access that data. And we want to be able to access that data from our cloud compute instance here. Now remember, we can only do that if our cloud compute instance is in the same AWS region as where all the NASA data is stored in the Earth Data Cloud. That's US West 2. CryoCloud's set up to do that. We don't really need to think about it, but it's worth remembering. Now, up to this point, everything that I've gone through using Earth Access, you could do from your local laptop, or you could do from the cloud. It's no different. And if we were working on a local laptop, we could use Earth Access download, and that would download these 4 files to our laptops. But I want to be able to access that data directly in the cloud, and we have to do a little extra step in order to be able to do that. Right? Normally, if the data was stored on our hard drive, on our laptops or on a workstation, we could just use X-ray to open this data, no problem. But because that data is in the cloud, we have to do an extra step. And the reason you have to do that is because cloud data or cloud storage is object storage, which is different to the way that files are organized and stored on your local laptop, which is a POSIX compliant, I guess, guidelines for how your laptop interacts with its file system. And POSIX is a very rich set of file functions for accessing data. Object storage has a very small set of functions, and POSIX can access blocks of data or even individual bytes of data within a file and return those. Object storage, you have to grab the whole file. And so the way we get around that is we set up a virtual file system on our compute instance, which allows us to use these POSIX compliant file functions to access the data. Now, that's a little bit of computer science that you really don't need to think about because Luis has taken care of it for you, but it's worth knowing that there's a fundamental difference between the way that the files are stored. So we're going to open this virtual file system on our computer using Earth Access, and we just need to feed it that list of results that we got. And This is always the gotcha, right? I once read that having pluralized variable names when you're coding is not the best practice, because you're always going to forget that what you pluralized and what isn't. So there you go. Fall into this trap, and I always fall into this trap because results for a list of things just make sense. But I have to remember. Right, so we've now opened these files. We can now use Xarray to open that data set. I'm just going to open one, and I'm going to open the second one on the list because I know that has more data to show you. And if we're using Xarray, we have to feed it another keyword called group. The HDF5 file format is a hierarchical file format. The data is organized into groups. Xarray can actually only read one group of data at a time. So I'm going to read GTL or Grand Track 1L, and I want land ice segments from that. Well, that's opening. Once that is opened, and it's probably going to be slow because you're all trying to do the same thing as me. Okay, that's opened. We can use just type in DS for the data set that we returned, and we get a nice little rendition of what is stored in that data. And you can see that we've got quality summaries, we've got H_LI, which is actually the land ice height. If you're not familiar with Xarray and the way it gets rendered in Jupyter Notebooks, you can click on these little file icons here and see what's going on. Sure.
Where does the potential list of keywords for the groups live?
I will get on to that. It lives either in the user guides that we have on the landing pages, but I'm going to show you a way of getting that potential list of variables using IcePix.
Wonderful, thank you.
But thank you for the question. Okay, so quickly to wrap this up, I just want to plot and look at this data, right? And I'm going to plot the land ice height using HVplot, which is a really nice tool for looking at big data sets like ICESat-2. I'm going to plot it as a scatter plot because it is, after all, mostly points. And I'm going to set the size of those points to be 2. Don't ask me 2 what, but 2 works quite well. And that gives a nice plot of the data. Now, the good thing with HVplot is it's actually interactive. I can select this icon here with the magnifying glass and highlight a section, and we can zoom in to various sections. So you can actually see the data. You can get all the way down to individual points. And then if you need to go back to the original view, do that. You got this little slidey button here. So that's really kind of Earth access, a very simple way for searching for data. In fact, what I've taken 30, 40 minutes to show you can be achieved in 3 lines of code, which is wonderful because before Earth access and IcePix came along, there were many, many more lines of code and lots of pitfalls. And Jessica talked about this yesterday. So I'm quickly going to go on to introduce IcePix. And here we're going to import IcePix. And if I don't want to type IcePix all the time, I'm going to use IPX. I'm going to still use Earth Access because we and you, if you're really interested, are still working on making IcePix so we can interact with data in the cloud. So I'm going to import, and at the moment we're using some tools from Earth Access to enable IcePix to work with data in the cloud. So I'm going to use Earth Access. I'm going to show a slightly different way of getting at opening or reading the ICESat-2 data using H5Py. There are other tools available that are perhaps a little more efficient. We're going to be working on some of those to try and put those into IcePix again this week. So if you're interested in how that's being done, come speak to us or join the group. And if we get to it, I'm going to use GeoPandas as the data structure to put that data into. It's a geospatial data frame, similar to the way that Pandas organizes its data. In fact, it's built on top of Pandas. It just adds the geospatial to the Pandas, hence the name. And you can think of it as essentially an Excel spreadsheet with geospatial information. So it's a table. And we need to also import some way of creating that geometry. And I'm going to use Shapely to do that, which is a package for working with vector data. And we're going to create points using that. So, and you'll see we're getting a user warning here. This is just because there are updates to Shapely and GeoPandas. And so it's telling me that I might need to do something different in the future. We don't need to worry about that warning right now. We're going to search for using the IcePix query object. And we're going to search for exactly the same data as we did in the last example, HL06. The keywords are a little different. Here, product rather than short name, spatial extent rather than just spatial, and the gotcha is actually, you know what? I'm just going to cut and paste that from my earlier search. IcePix expects a list, so we're going to change that. It will shout at you if you don't give it, so you'll know you made a mistake. And we set the date range using those date strings. And now this just returns a query object. It's a set of results. We can get information by that about that just by looking at the granules that are available to us. Using this avail granules method. We're not going to call it grand ID. We're going to call it gran ID. Keep track of your grandmothers, people. And that tells us we've got 4 granules, total of 21 or average size of 21 megabytes, total of 86 megabytes. We can do other searches, right? We talked about reference grand checks and cycles for ways of identifying ICESat-2 data. IcePix allows us to do that kind of search by setting cycles. And I happen to know that cycle 6 and tracks, we're only going to enter one track, 1142, essentially returns the same data. In this case, I'm just grabbing the first available granule for this. Now, we can look at the S3 links by doing another call to this result. And another call to available granules. But this time, we want to search for stuff in the cloud. So we're going to say cloud equals true. There you go. This is why you don't use plurals. Right. So that returns an S3 link to that data. Now, you can see that this is actually a nested list because you've got 2 square brackets. I'm just going to fix that problem by just returning the first element of those results. So it's just a single list. That will just help me remember this. Now, the way we need to do this, to access this data using IcePix, is to log in, although I think because I logged in earlier, it will remember this, but I want to make sure that I get an S3 token. And there you go. It tells me that I'm using this, and we want to create that virtual file system. We're going to use Earth Access to do that because currently IcePix does not have that capability. It might by the end of the week. And I need to say that I want to get this data from NSIDC DAC. That's returned. Now, we do exactly the same opening of files into the virtual file system. I'm only going to open one of them. And in this case, because we're using a lower level library, we actually have to tell this S3 object, this virtual file system, we want to open these files in read-only mode, and we want to open them as just a byte stream. So we don't want to do anything special with the data. We just want to get the bytes back and put it into this variable file. So we do that by saying RB, which just says open it read-only, open it as bytes. And then I'm going to open that file, or read that file, I should say, using H5Py. I'm going to open it as a read-only file. And you can see here, this is not as much information as gets returned from by Xarray. It's just tells us what the object is. In fact, this is just a file handle or a group of the HDF files, and it says it's pointing at this particular file name here, ATL06, whatever, .h5. Now, in the interest of time, I'm gonna stop and hand over to JP. But the rest of the tutorial shows you how to access the groups within that H5 or HDF5 file. So you can then start to work at it. What HDF H5Py does is, rather than returning X-array objects, it just returns these NumPy arrays, right? Which is actually what X-array has inside that data set object, but it's just an array of values, not as rich an object with attributes as X-array. But it's a good way to get at some of the data, and you can put that into X-array. You can put it into a GeoPandas object, or there are other data structures out there that you could utilize to work with that data. So I'm going to yes, yeah, thank you. I will do that. Yeah, oh yes, thank you. Actually, I will skip to that. So so we had a question about how do we get a full listing of the variables. So we can use IcePix and the result object. That was the German order. And vars.avail. So here I'm saying I want a list of variables that are in the ATL06 data sets. And it gets returned as a list. I'll show you what that looks like by just looking at the first 20 there. So you can see that there's this structure here. And there are a whole load of groups. We've got ancillary data, and then we've got all these data sets underneath that. In fact, if I do, this is another way of getting at it. If I use file handle keys, you can see that under that first group, under FH, there are a whole bunch of groups, ancillary data, then groups for each of the beams, and a quality assessment group. Now, this returns the full list. In fact, we can use length to see how many there are. So there's 594 variables packed into that ATL06 file. You would have to go to the user guide, go to the ATDB, algorithm theoretical basis document, BD, sorry, to find out what each of those are. There's also a data dictionary associated with each of the ICESat-2 data sets, so you can find out what those variables are. And I'll just show you this quickly, if you wanted to just get a subset of that, you could do something like this. So I want to get, what I want to do is create a Python dictionary of the name of the variable, and I'm saying that this last part after the last forward slash or backslash, depending on how you look at it, that's going to be that's the name of the variable. So I want to get that by using split, and then split returns a list, breaking it on every single one of those forward slashes. I want to get the last one, which I can do quickly by saying -1, which is the last one. I want to get the path to that, and I want to go through var list to just look at every single one of those 594 variables and do that. But I don't want to get everything. I just want to get everything that starts with GTL or GT1L. So I can say var starts with GT1L, And you can see here that I've got a list of all the variables that fit under that within that group. And there's a lot of subgroups in there. I could take this actually and just say, you know what? I just want everything that fits directly under that group, no subgroups. And the way I can do that is to say, and I'm going to do this where I count the number of forward slashes, and I only want to get those forward slashes that are or those path names that have 2 forward slashes. And you get nothing. What did I do wrong? Oh, yes, yeah, and I need to, in fact, there we go. That works. So there, I've got all of the variable or data sets within that GT1L land ice segments group that only sits within the top 2 levels. And you can play around. I'm trying to work on something that allows you to do that a little quicker and a little more effectively. But I'm going to hand over to JP.
Any questions at this stage? Just checking in with folks before we continue on.
If you're using the Earth Access Python library, are you able to get download links for subsetted granules?
Can you repeat that again? Sorry.
If you're using the Earth Access library, can you get like download links to get subsetted granules?
No. IcePix also allows the subsetting, but that can only be done on data that is stored at the DAC.
So through the API.
Yeah.
Right.
So so stuff that's stored in the cloud currently cannot be subsetted. In fact, we're going to be working on that this week to try and introduce that capability to IcePix.
All right. Thank you.
All right. Or at least figuring out how we can do it.
Okay, yeah, so my name is JP Swinsky. I am the lead software developer for Slide Rule. There's a bunch of team members here, so that all are part of the Slide Rule team. So there's Tyler that you know, David, and Scott. And Scott over there. Yeah, and we also have Ben, a couple others, back at Goddard, Carlos and Eric. And I apologize if I missed anyone. So I guess I just wanted to give a quick overview of what Slide Rule is and then what it can provide. So I've got the main thing though is put together a tutorial. It's right under the data access formats tutorial that does an overview of the functionality. So you can look there and kind of see some of the main things, and I'll be going through this just a little bit. I won't go through the whole thing, but just to give you a taste of the things that we support. So I guess the most important thing to know though is that I know that you're always supposed to read documentation before you ask questions. Like that's the right thing to do. I hate documentation. So please don't ever feel bad just asking me first. Like you don't have to have looked at anything. That's how I operate. So yeah, so that's the most important thing. If you do like reading documentation, we do have some links right at the beginning of this tutorial for all our docs and our repos and things like that. So what is slide rule? So slide rule is like the complement to what Andy was talking about. So there's a lot of tools that run on the client side, on the Cryo cloud that you're interacting with directly. And then those tools can go out and access other services. So like CMR is one of the services that you would access through tools like Earth Access and IcePix. And we want slide rule to be, again, one of those other services that you go out and access. And the service that we're providing is we have data processing code that the UWF team has defined and designed, and we run that on servers in US West 2, right next to the data. And so you can ask us through requests to run that data processing code and just return you the results. Now, why would you want to ask us to do it? The main reason is that we can do it at scale very quickly. So a workflow or an idea of where a slide rule would fit in is you have an idea, you're working in your local environment, maybe you've prototyped some stuff in Python, and you've gone out and you've downloaded a couple granules, you've worked with those granules, you have an idea of how you want to work with the data, and you find out that, well, it works really well, but on your single machine processing one granule, it takes 10 or 20 minutes or 30 minutes. And then you find that you want to run it on 23,000 of these granules, or, and that just becomes untenable. So we've tried to find parts of the workflow that are data processing intensive, that are just compute intensive or IO intensive. And we've tried to pull those off and provide those types of functions in slide rule where we can run them at scale and then just return you the results, so that your higher level logic, you can focus on the higher level logic of analyzing the data and not worry as much about the lower level data access and crunching through photons and things like that. So, and I do want to just take a second and plug that if you have algorithms that you would like to see run at scale in slide rule, please work with us. At any level. If it's just saying I have a great idea or I have some code that I'd like to get in there, we're very open to that. So being a bunch of servers running in the cloud, it's kind of a pain if you were to try to access them directly, it'd be kind of a pain to do that. So we've provided clients for you. So we only have 2 clients right now. We have a Python client and we have a Node.js client. But primarily for like the purposes of this week, we can just focus completely on the Python client. And the Python client gives you an easy way to send those HTTP requests to the servers and process the responses back. So it just kind of wraps them in Python functions. And so our client has a handful of modules in it. And they're listed right here under this first section in the tutorial, import and configure. So the first step would be importing the slide rule client. I've just kind of listed a whole bunch of the modules. You only need to import the ones that you use, or you can just import them all so that they're all available to you. And once you import the client, you can begin using it immediately. You don't have to configure it necessarily. But though I do recommend having one line at the top that does initialize the client. And this is just a good placeholder so that when you go back and you do want to change certain configuration parameters, you have an easy place to do it. And you'll notice, so I've tried to link where in the documentation all the parameters are documented for the different functions that are being shown here. So if you go back to this tutorial, you're like, what parameters are available? You can go and look it up and it'll take you right there. And so you can see these are the different parameters we have in the initialization function. So in this tour, I've tried to divide it up into some of the core functionality and some of the advanced functionality that we provide. So the core functions are listed here. And for each one of them, I have a write-up of what it does, and then a little code snippet that shows it being used. So the first thing, a part of the core functionality is just reading HDF5 data and some NetCDF data sets directly. This wasn't necessarily what Slide Rule was designed for, but with this, where we are right now, where we're transitioning a lot of data sets into the cloud, until we get all of the tooling built up to be able to access that data sets directly, until we get some cloud optimized formats that are easy to access directly, we expose direct access through our servers that you can take advantage of. So for instance, if you, in the H5 module of the Slide Rule client, you could do something like this. You could say, I want to read this granule, and I want these data sets. And Andy had just, gone through showing you how with IcePix you could list the different variables in that data set. So, well, I want the first 10 latitudes and longitudes for each of the ground tracks in this granule, and you can make a call here and directly read it. Again, it wouldn't necessarily make sense to do this for a small read, but if you were reading many granules and you were actually had some, and you were doing multi-processing on your client side, you can envision that you could be reading a lot of data, and this would do the heavy lifting of reading that data and returning it to you very efficiently in a parallel way. So like one of the things that you get is that all of these reads are done at the same time and then passed back to the user. So then you would just get a dictionary of NumPy arrays. But moving on from that, the next level of service that we provide is we do provide some subsetting of some data sets. So we are mainly focused on ICESat-2. And so the main subsetter that we provide is subsetting the ATL03 photon data. Again, if you want to look at all the things that you can do with this function, there's links to the documentation that you can click on, and it'll take you to all the different things that we support. But just getting a little snippet of how to do that. The main, I guess, we support a couple of different ways of defining the region of interest that you're looking for. Maybe the easiest way is just creating a GeoJSON file of that region, and then you can pass it into this function called the toRegion function in the Slide Rule client, and that just manipulates it in such a way that it's easy to send up to CMR, and it's easy to send to our servers. And then you'll provide the output of that function into a parameter request dictionary under the poly key. And then there's a handful of other parameters that are optional to provide. In this case, I didn't want a lot of data. If you're going through this notebook on your own, I didn't want to subset a lot of data. That's usually a good idea with ATL03. It's really easy to consume all the memory on your machine by asking for like 100 granules over a 100-kilometer region. Like that'll immediately take down your local client. So I would keep ATL03 subsetting requests to smaller sections. And then you can see here, I've defined a 20-meter length for the segment and a 20-meter resolution. So we provide customized segment lengths. And this is saying create a segment every 20 meters and then step 20 meters. In the ATL06 product, it's actually and Tyler, you'll correct me if I'm wrong, it bases off a 40-meter length, right? And it steps 20 meters, so there's a 20-meter overlap. So you can go down as small as you want, or as large as you want. You can make this 500 meters, you can make this 5 meters, whatever makes sense. And so in this case, I ran the request, and then returned the data in a geodata frame. And so here I will point out to you that we have predefined a set of variables that come back in the request, and we put them in a geodata frame for you, and it's provided here. The columns are the variables that we read; those are hard coded. We do provide an ability to include ancillary fields in your request, and that's in the advanced functionality later in the tutorial. You can look at that if that's something that you're interested in using. But we've kind of chosen a predefined set that we think covers most use cases. Another thing I'll just point out here is if we look down at the size of the data coming back, we only have 1,000 some rows. So each row is a photon in the ATL03 data set. And that seems kind of small. And so when I was doing this, this is exactly the path that I followed. I was like, oh, that's kind of small. And so I took a look in the original data, and there's about 300,000 photons in this segment that we requested. And so I then went back and was like, oh, there are other default parameters that are going to filter this data set. So that's a common thing that if you're working with slide rule, a lot of times when you change the default parameters, there's other parameters that need to also be changed to make sure that the request makes sense. A lot of times the easiest way is going to be to like find myself or find Scott or Tyler or someone and just ask them, like, hey, there's not as much data coming back. Do these parameters look reasonable? Is there anything that I need to change? In this case, it turned out to be we do filtering we look at each segment and say how many photons are in the segment. And if there's too few photons, we'll throw the segment out as not being valid. And I hadn't changed that parameter. So then building on top of that, so the first API was just reading the data directly. The second one is subsetting the ATL03 data. And then this third one is now generating custom ATL06 elevations off of the subsetted ATL03 data. So if you don't want to deal with the photon data, but you want an elevation product that is either over a region that ATL06 doesn't provide data for, or has characteristics that are slightly different than the ATL06 data. For instance, you want a shorter length segment. You want to generate an elevation every 10 meters. You can use slide rule to do that. So this is the same request. If you look at it, it's very similar to what is up here, but there's a couple differences. So the first difference is I've taken out the RGT in the cycle because I want all the granules that are in this region now. I think it's like 106 or something like that. Yep. And I caught my mistake and updated the filters. So for a 20-meter length segment, I bumped the minimum number of photons that are required for a valid segment down to 10. And I said that the minimum along track spread of the photons in that segment is now 7. And that was a correction to make it so that it's reasonably set for this length segment. And now I run the ATL06 function right here. And that goes out, makes the request to slide rule. Slide rule pulls all the granules, does all the processing in parallel, returns all the results back to a geodata frame that you have here. And the columns here try to match the main variables found in the ATL06 standard data product. And so you can see here, looking at the whole region of interest, there's just over 500,000 elevations calculated from all the photons. So there was probably hundreds of millions of photons that went into to calculate this data. And I'll point out again, if you want to look at all the different function parameters that go in, you can follow the link to the documentation. Moving on, you could say, well, in addition to creating custom elevations, I also want to pull in the ATL08 classification data. And so we have the ability to do that as well. And you can see with the addition of this parameter in the request, the ATL08 class parameter, you can say, when you go and calculate those elevations, I only want to look at the photons that refer to the ground. Or there might be other requests where it's like, I want to see the top of the canopy. And so you would then specify, I only want to use canopy or top of canopy for it. I won't go too much further than that. I'm just going to highlight a couple of the other things, and then I want to take 1 second to just give you a quick look at the layout of our documentation. So we do, in addition to the ATL06 algorithm, we also have an algorithm. We worked with the folks at UTexas to integrate their the algorithms in their faux real software, so we can calculate vegetation metrics as well, and that's found under the ATL08 function. And then we have the ability to go and sample rasters at each of the calculated points that are returned. So if you wanted to do you want to generate custom elevations using the ATL06 algorithm, and then you wanted to go and sample the Arctic DEM at every point an elevation was calculated. Well, you could specify, actually, I chose one that you could specify the Arctic DEM as in your request as being sampled, and it would go out, and then for every elevation calculated, it would go and find the right tile and do the sampling of the Arctic DEM, and then correlate it in the same row in your data frame. And in this case here, I think I chose the Landsat HLS product and the JEDI level 4B product, and I was doing an ATL06 call. And so then that would go down, and you can see here, for every elevation calculated, we now have a couple columns associated with the Landsat data. And so here's the time of the Landsat data that it was measured, and then this is the value, and the same with JEDI, and it's all correlated in the data frame for you. And then lastly, we do provide some subsetting for the JEDI product as well. I will stop there and just say that, we also have a handful of other more advanced functions. You can look at them there. If any of them look like something that would be applicable to your project, please reach out to me, and we can go through it together. But the last thing I wanted to do is just to go through the documentation. So the documentation is divided into two main groups. We have user guide information here, and then we have the API reference here. And we're building up some tutorials down here. So a lot of times, if you want to get the big picture, it would be in the user guide. So here, for instance, if I go to the ICESat-2 plugin page, it shows all the different parameters that can go into your requests, and it tries to describe what they are. But then if you're like, well, I know what parameters I want, I just want to know how to make the function call, then you would go to the API reference. And here we have all the different functions and how to make those calls. Okay, I'll stop there.
We have time for a couple of questions.
If I'm using slide rule to subset ATL03, let's say I'm interested in like the geophysical corrections or any of the other data sets, is there a way to get that through slide rule with it, or do I need to find that somewhere else?
No, subsetting, yeah. So subsetting ATL03 is one of the functions that we provide.
But it does return like a geodata frame, right? Of just like at the photon level.
Yes.
So say I'm interested in the geoid or along that track. Can I get that?
Yeah. So we provide right now, we provide the ability to request some ancillary fields from the original data sets, and we'd have to work together to make sure there's the ones that are supported. That's a request that comes a lot, and so that's something that we're adding in more and more capability to. So it would be whether or not the field that you want is in one of the groups that we support. If you're familiar with ATL03 data, the way it's structured in the tree, it's not always easy to correlate every data point to a photon. And so we've built that for some of the groups, but not for all of them.
Right. Cool. Other question real quick. If you're pulling out data with, say, REMA or the Arctic DM or the Landsat HLS, will that pull out the strips or like the closest granule of the Landsat?
There's a couple things that you can specify. Yeah. So if we support the strips as well as the mosaic. If you do the strips, those requests can get real big real quick. So you just have to be aware that a small request could take a long time and return back a lot of data. I can work with you on exactly how that would all come back, but in our documentation, actually I should have. Yeah, so we have, these are the data sets that we support. This is a list of the data sets that we support here that can be sampled. And so it would be for you if you're looking at the REMA strips, and then there's a handful. Let me see if I can. Yeah. Right. And if you can provide a time, and we can choose the closest strip to that time, or you can provide a range, and we'll only do the strips that fall within that range.
Sweet. Thank you.
This is a question about this, and also just kind of some of the general resources, like cryo in the cloud. What is the sort of lifespan of these products that you're anticipating? Like, how long do you expect this service to exist, and that sort of stuff?
Forever. So slide rule. So for the client side stuff, the great advantage there is that they should exist as long as the services that they rely on are operational. So for IcePix and Earth Access, they will always work as long as the services that they are working with work. For slide rule, it's a little different because it takes a lot of money to run a lot of nodes in the cloud and chunk on all the data. We're funded through FY24. So we should be around at least that long, but we're always looking ahead and trying to make sure that we can keep the services running. With slide rule, it doesn't need to be continuous. So we're all open source. So in theory, if there was a workflow that you really relied on, you're like, listen, I need this for the next 5 years. You could recreate what we've done. It's all openly available. We've tried to do our best to make that a reality, not just in theory, but also in practice. Though I'm sure it'd be working with us to help you get another instance set up.
One last question over here.
With all these capabilities from slide rule, do you think that it could become kind of like a core service for the ICESat mission, or NASA to say, this is going to be the subsetter? Because there is not such a thing in the cloud right now. If you want to subset, the only services are available for on-prem data. So do you think it will be like a possibility?
That sounds great to me. That would be over. Yeah, that would be a conversation probably with David and Tom. That would be a conversation to have with them.
SlideRule provides on-demand custom products, right? And the reality is there's a lot of core products like ATL06 and ATL08 that work really, really well. Like that solves most problems for a lot of people, but sometimes it doesn't solve the problem. So my personal vision is kind of a hybrid approach where missions can prepare some standard data products, but then the higher level products, the custom products, can be generated with a service like SlideRule. So I don't think SlideRule is the answer, but I think it is an answer in this kind of realm of what we need for future missions and data delivery.
There's also something that JP and David and I have talked a lot about, switching kind of how missions work on their head, going directly downlinking from the satellite to AWS, which is kind of how NISAR is planning, and then having all the compute for that mission in AWS, and then having things like NSIDC and DAX being services off of that, and then SlideRule being a service off of that. So when you switch everything to be cloud first, you can have these things as services built around that.
So right now you're running a server, right? An API server to actually do the subsetting. And as we've talked about, like, and some of the things that you all have said have colored my opinion about this or my thoughts about this, but do you foresee that you could create a cloud optimized data format that you wouldn't need to run a server? What I've seen so far being sort of new to ICESat-2 data is that there's obviously a hierarchy and complexity to this data. So do you think, I guess, question for the group, like, do you all think some sort of cloud optimized data format is possible potentially through like data tree that would be worth providing? I do recognize that maybe we'd still need some sort of server for the archival formats, but at least, or for the original raw data, but then could we also create a cloud optimized data format that we think, could negate the need?
That's a great question. And it really strikes at what we're trying to accomplish with SlideRule. So when we set out, we never intended for SlideRule to be used to read the data. Reading the data was just the first problem that we needed to solve. So we spent, half a year to a year solving that problem because it was what we needed to solve to get to the stuff that we really wanted to do, which was the higher level customized data products. So our goal, ideally, data in cloud optimized formats would not preclude higher level services. It would just make it easier for those higher level services to run so that they wouldn't have to solve this data access problem. So when cloud optimized HDF or Kerchunk or some of these other solutions come into play, we're going to plug it right into SlideRule, and it's going to just make us faster. And we're going to be that much more efficient. And it'll be easier for other groups to do the same. The reason why we think that there's always going to be a need for these service-based higher level products is that it's not necessarily the fact that the data is not in a cloud optimized format. It's that even when you have it in a cloud optimized, it's massive. And it is not practical to run tools right now like Python to do higher level processing at scale. That's not efficient. But we think what is efficient is to use tools like Python to do the higher level processing and analysis and offloading the boring stuff to these types of services. Where, taking ATL08 and classifying each photon, or running a customized YAPC where you have to create a window around every photon in the cloud and then calculate distances to each one and produce a weight. That's very easy to say, and you could define it in 25 lines of Python, but then to run that on 100 terabytes of data is then that becomes like a computer science problem. So we can run those types of things at scale. And, like Dave was talking about the different sampling techniques, he can specify those things and we can run those techniques at scale and then just provide the results to users that can then go and do the higher level analysis that's more applicable to their application.